So in this video, we're going to continue with nomenclature of alkanes and specifically cycloalkanes. We also have some special alkyl groups that we didn't cover in the last video. So cycloalkanes and our special alkyl groups. So I'm going to go back out to that handout that I have posted on Canvas for you guys, the nomenclature handout, and then scroll down to the next page. This one's on cycloalkanes. So we're going to do this similar to what we did last time. I'm going to kind of read through the rules and then I'll go back to the whiteboard and we'll do some examples. So naming cycloalkanes is going to be very similar to naming straight chain alkanes with just a couple little differences. The first one, we have to indicate that it's cyclic. So we're going to put cyclo right before the parent name. So if I was to draw, let's say, a chain of 5 carbons, right? 5 is pent. And then it ends in ane, right? Because it's an alkane. If I was to make a ring of 5 carbons, 5 is still pent, it's still ane because it's an alkane, but I'm going to put cyclo in front of it. So cyclopentane. So directly in front of our parent, we're going to put the word cyclo. Even if I have substituents on it, cyclo goes right in front of it. If I go down and look at these couple examples that I have, right? I have 6 carbons in a ring here. I have cyclohexane. Here I have 5 carbons, the next one, cyclopentane. So cyclo is going to go right before the parent name. My second rule, we always want to start numbering it, and this is the same rule we had before. We want the lowest numbers for my branches, right, for my substituents. Which means if I have one substituent on my cycloalkane and only one substituent, that substituent's always going to be on carbon 1, right? If I go back up and look at these examples, remember if it's straight, we want to start numbering closest to that substituent or at the end closest to that substituent. We always have to start numbering it on an end. So I would start numbering it here, right? I can't make the carbon that I just made 2, 1, right? I have to start at the end, but I want to start at the end closest to that substituent. We want that substituent to have the lowest carbon number possible. However, a ring doesn't have an end, right? So if I put my substituent here, right, I'm putting a methyl group there, then that's going to be carbon 1. If I was to put that substituent here, now that is going to be carbon 1. No matter where I put that substituent, I always want to number it so it has the lowest number possible. It's always going to be on carbon 1. So if you have one substituent and only one substituent, as soon as I have more than one, I have to say where they are. But if there's one and only one, I do not need to state where that substituent is. So like if I was to name this guy, right, I now have a branch on it. Instead of saying 1-methyl cyclopentane, I can just say methyl cyclopentane. I don't actually have to put that 1 in front of it. If I put the 1 there, it wouldn't be incorrect. It's just not needed. It's like in algebra, right? In algebra, x is actually 1x. Putting the 1 there isn't wrong. It's just not kind of how we do it, right? It's just weird. So if you want to put the 1 there, you can. It's not incorrect. It's just not typically how we would name them. And then again, just be careful. It's if there's 1 and only 1. As soon as I have more than one substituent, we need to put numbers for all of the substituents. I still want to number it. I'm still on rule 2 here. I still want to number it so I have the lowest sum of substituents. One of them will always be on carbon 1. And then we use, the normal rules. If it's the same from either direction, then we number them alphabetically. So let's go out and do a couple of examples. And I'm going to put a bromine and then a 2-carbon group. So we're going to name this. Our parent is going to be our ring. I am going to talk about an exception after where if it's a cyclic structure, the cyclic group is not the parent, but most often it is going to be my parent. So if you wanted, you could go and highlight it, circle it like you normally would, but that's my parent. So the substituents are the things hanging off of that ring. We're going to number it. We're going to follow the rules that we were using before. We want the lowest numbers. And one of my substituents will always be on carbon 1, the other will always be on carbon 2. So if I start at the top and go clockwise, I'm going to get 1 and 2 for my numbers. If I start here and go counterclockwise, I'm still going to get 1 and 2, right? We want the lowest sum. The sum is the same either way. So this is where we're going to use the alphabet. So this group is a 2-carbon group. 2 is eth. It's a alkyl group, right? A carbon substituent, so ethyl. This is bromine, which is bromo when we name it. And B comes before E in the alphabet, so we're going to use those pink numbers. We list them alphabetically, same as before. So 1 bromo, 2 ethyl, make sure you put dashes between numbers and letters, and then cyclo, and then there's 6 carbons in that ring if I would have continued my numbering. 3, 4, 5, 6. 6 is hex, and it's an alkane. So 1 bromo, 2 ethyl, cyclohexane would be our name for this one. I do want to go out and look at those special alkyl groups right now because I want to start using them in some examples. So I'm going to scroll back up to the very first page. This thing is getting messy. And the only box we haven't considered yet, the one in the middle. And these look kind of weird. They're easier to see them when they're on rings. They don't have to be on rings, but they're easier to see on cycloalkanes, and that's why I want to do them now. So we're looking at this box. Let me erase some of the other things here so it's not so hard to look at. So again, what these are, so maybe it's easier. I'm going to draw a cyclohexane, and then I'm just going to put a propyl group on it, right? Prop is 3. We go up and look, prop is 3. So these 3 carbons that I just put on there would be a propyl group. If I was to draw another one though, and I draw it like that, that's still 3 carbons attached to it, right? There's a carbon here, here, and here. So that's 3 carbons. This is 3 carbons, 1, 2, 3. So what the heck do we call this, right? It's propyl because there's 3, but we can't call it propyl because this one's propyl and they have to have different names. So what this is it's an isomer of propyl. Because it's an isomer, remember isomers have the same, they're connected differently, right? Same numbers of each type of, same number of atom of each type of element, right? 3 carbons, same number of hydrogens. But they have different structures. So this is an isomer of propyl, so we are going to call it isopropyl. So if I go look at my box here, this is my parent, and then I'm saying where it's attached to my parent, it goes out to a carbon, and then that branches to a carbon. That's what we just drew down here. The name of that group is isopropyl. We could do the same thing with a butyl group, right? If I was to take, we'll just use this and put 4 carbons on it, that's butyl. If I was to take one of those carbons and move it, it's now an isomer of butyl, so isobutyl. So again, this is the parent, this is where it's attached. There's 2 other ways we could do 4 carbons, and that's what these other 2 are. We can't call them all isomers because then that would be confusing. So one gets to be an isomer of butyl. These other ones are isomers, but we have to call them something different. So sec-butyl and tert-butyl. I will do examples on the other page, and I'll explain more kind of how to tell. While we're here though, when we're alphabetizing these, we are not going to use sec and tert for alphabetizing. We are, however, going to use the I in iso. And if you look at the names of these, the sec and tert-butyl have a dash, right? There's a dash between tert-butyl and sec-butyl. If I look at iso, there's no dash, and that's kind of how I remember it. Also, the sec actually stands for secondary, tert actually stands for tertiary, which are representing numbers, and we don't alphabetize numbers. So whatever you have to use to help you remember that, the sec and the tert don't count for alphabetizing. The I's, however, do. An example? Chlorine. Okay, so we have a cyclic structure. Unfortunately, I did cyclohexane again. They're the more common of the cyclic structures, by the way. We're going to spend quite a bit of time on cycloalkanes next week. I just kind of, by default, if I'm drawing something cyclic, I tend to do a cyclohexane because they are so common. So we're going to number this. Remember, we want the lowest numbers. So I know I'm going to start here, right? Because then they're going to be 1 and 2. If I were to start with 1 here, then my next substituent would be on carbon 3. Sometimes you just have to number it all the different possible ways and add up. But once you've done it a few times, you can kind of see the pattern. I'm going to start with the propyl group here, 1, 2, 3, 4, and go in this direction, because then there's only 1 carbon between this substituent and this substituent as far as getting my branches. If we went the other way, we will do it. I would have 1, 2, 3, 4, 5. So my branches would be on 1, 2, and 5, which adds up to 8. The pink numbering, they're on 1, 2, and 4, which adds up to 7. So it is the pink numbers that we want. Kind of often the biggest pain in the butt about cyclic structures is just figuring out the numbering. So lowest sum is always our goal. If the sum is the same, like it was in our first example up here, then you use the alphabet. But lowest sum always first. So naming these guys, I have a chlorine, so this is going to be chloro. This is 3 carbons just in a straight chain, so that's just propyl, right? If they're in a straight chain, it's just the normal prefix, so propyl. And then this one is 4 carbons. 1, 2, actually let's use a different color so it doesn't get confusing. 1, 2, 3, 4 carbons. So I know it's one of my forms of butyl. And the way I remember this one, if I'm to number those carbons, it's actually attached on the second carbon. So that's going to be sec-butyl. If we go back to that handout, my sec-butyl group, right, it's attached on the second carbon. 1, 2, 3, 4. The sec actually stands for secondary. And what that really means is that this carbon here, where it's attached to the parent, is attached to 2 other carbons. It's attached to this carbon and this carbon, so it's secondary. We could look at tertiary that way when we're here. Tert stands for tertiary. The carbon that's attached to the parent is attached to 3 other carbons. If I look at the iso one, the carbon that's attached to the parent is attached to 1 other carbon. That carbon is attached to 2 other carbons, but we're looking at what's directly attached to the carbon that's directly attached to the parent, if that makes sense. So going back, this is a sec-butyl group, right? This carbon right here, my yellow highlighter, is attached to this carbon and this carbon, so sec-butyl. It's also attached to the second carbon in that 4-carbon chain. So whatever works for you for trying to remember that. So when we put the name together, we are going to follow the alphabet. So remember, we are not alphabetizing sec-butyl based on sec. We're alphabetizing it based on the B. So that one's going to come first because B comes before C and P in the alphabet. So 4 sec-butyl, 2 chloro, because C comes next, 1 propyl. And then I have 6 carbons in a ring, so cyclohex, and they all have single bonds, so ane. So 4-sec-butyl, 2-chloral, 1-propyl cyclohexane. Remember, when we're listing these, we list them alphabetically. That's a really common rookie mistake, is to actually put like the one that's on one carbon first. So they would do 1-propyl, 2-chloral, 4-sec-butyl, like do them in order. That's not how we list them, right? Our rule says we list them alphabetically. We're not alphabetizing based on the S in sec-butyl, we're alphabetizing it based on the B in butyl. Let's do another example. Do something different. I almost drew cyclohexane again. I'll make this one kind of messy. Okay. So numbering, again, always kind of the first challenge. Anytime you have two substituents on adjacent carbons, you want to start with one of those two. And then you want to figure out which way you're going to go. So if I go this way, 1, 2, 3, 4, 5, but I have substituents on 1, 2, and 4. If I start here, 1, 2, 3, 4, 5, they're on 1, 2, and 4. So it's the same from either direction. So now we need to pull out the alphabet. So we're going to name these. This here is an isopropyl group. I have 3 carbons, but they're not in a straight chain. This one over here, I have 2 carbons, so ethyl. This group, the one that's unlabeled, the one on carbon, pink carbon 2, green carbon 1, what is that one? Yeah, isobutyl. There's no dash between the iso and propyl and iso and butyl. It's the sec-butyl and the tert-butyl that have the dashes. And then for these ones, for alphabetizing, I do alphabetize the I. So iso gets alphabetized. The problem is what I'm choosing between are two things that have iso in them. So the I is the same, the S is the same, the O is the same. So the B is the first place I get a difference. So isobutyl is going to come before isopropyl when I alphabetize those, which means this time I want to use those green numbers. So 1, oops, I almost did it. What comes first in my alphabet? Yeah, E. It's okay if you have to say your ABCs. A, B, C, D, E. So 4-ethyl. And then I have 1 isobutyl, 2 isopropyl. Again, make sure you have dashes between all of your numbers and letters. And then run all of your letters together, so no space between isopropyl and cyclopentane. Right, I have 5 carbons in a ring, so cyclopent. They all have single bonds, so it's an alkane, so it ends in ane. So 4-ethyl, 1 isobutyl, 2 isopropyl cyclopentane. That's a mouthful. So another example. Let's do 4. So this is going to be one of our exceptions where our ring is not the parent. So if I look at my ring, I have 4 carbons in my ring, right? If I look at the straight chain, this part, I have 1, 2, 3, 4, 5, 6 carbons in the orange highlighter. Since the 6 carbon straight chain part is bigger than the 4 carbon cyclic part, the straight chain part is going to be my parent. So whichever part is bigger becomes your parent. So I'm going to erase the highlighter on this, and then that's my parent. So I'm just going to use all my straight chain rules, right? I'm going to circle my parent. I'm going to number my parent. I want the lowest numbers for my branches. So I'm going to start here. 1, 2, 3, 4, 5, 6, right? So I have substituents on carbon 1 and 3. If I would have gone the other direction, 1, 2, 3, 4, 5, 6, they'd be on 4 and 6, which is obviously much bigger when I add those together than 1 and 3. The name of this group, it's a 1 carbon group, so meth. It's an alkyl group, so it ends in YL, so methyl. And then this one, any guesses as to what we would call it? If it was a straight chain of 4, right, it would be butyl, right? If they weren't in a ring, what do we do if it's in a ring? Yeah, good, we put cyclo in front of it. So that is a cyclobutyl group, right? I have 4 carbons, so but. It's an alkyl group, right? It's a carbon-based substituent, so it ends in YL, but it happens to be cyclic, so I'm going to go and throw cyclo in front of it. So this group is a cyclobutyl group. Listing them alphabetically, I do count the C. The C stands for cyclic, it stands for a word, not a number, so I'm going to alphabetize that. So 1, cyclobutyl, right? C comes before M in the alphabet. 3-methyl. And then I have 6 carbons, hex. And it's an alkane, they all have single bonds, so ane. So 1 cyclobutyl, 3-methyl hexane. The last part of naming that we're going to talk about is with our cycloalkanes. And hopefully you guys watched the intro video. So at the beginning of this module, I always do a little introduction. And in that introduction, I had some models. And one of the ones I showed was a cyclopentane. And I put 2 green atoms on it. And we could actually draw those where, and I'm just going to use methyl groups this time, where I have them both coming out at us. Remember, wedges mean they're coming out. So my ring is in the plane of my iPad, and then those 2 methyl groups are coming out at us. I could also draw it where the 2 methyl groups are going back. In either one of those, the 2 methyl groups are pointing in the same direction, right? Either both forward or both back. Alternatively, I could draw one where I had 1 methyl group coming out at us and I had 1 methyl group going back. That is actually different than when they're on the same side. Again, if you haven't looked at that intro video, please do. I have the models made in that video so you can see them. But having, the 2 groups on one side versus 1 group on one side and the other group on the other side actually makes these different. So the relationship between them, if I was to ignore, how they're pointing, it would be 1,2-dimethyl cyclopentane, right? They're the same molecule, they have the same name, but their orientation in 3-dimensional space is different. So these would be considered Cis Trans Isomers. These 2 are the same. So they're just, flipped over from each other, but those 2 are different from the one on the bottom. So these are given designation cis. I just remember cis, same side. This is given the designation trans. So they're opposite of each other. So if you have 2 groups and they're on opposite sides, trans. So this would be trans, and I'll write it down in a minute. Trans 1,2-dimethyl cyclopentane. If you have 2 groups and they're on the same side of that ring, cis. So the ones on the top would both be cis 1,2-dimethyl cyclopentane. So these guys are stereoisomers. We're going to look at other types of stereoisomers. Chapter 5 is all on stereoisomers. So there's different types, but the general definition is they differ only by their orientation in 3-dimensional space. basically, if you were to make models of the cis version and the trans version and then try to superimpose them, try to line them up on top of each other, I can't. They're actually different. This bond, because of the ring, I can't rotate them. And again, I do show that in that video. So I can't rotate these to get from one to the other, making them different. So these differ only in their orientation in three-dimensional space. That's our definition of a stereoisomer. The specific type of stereoisomers that these are cis trans isomers. So for di-substituted, so di meaning two, so di-substituted, cycloalkanes, we can have cis trans isomers. So cis trans isomers is a type of stereoisomer again. Stereoisomers being things that differ only in their three-dimensional orientation. Cis means the two substituents are on the same side of the ring so either both up, both down, both coming out at you, both going back, depending on your orientation. So cis, and then trans, the two substituents are on opposite sides of the ring. So going back up and naming those, I said I would write them down. I said them, went too far. So these two, same name, cis, and then 1, 2. If I went the other way, also 1, 2, right? They're both methyl groups, so alphabetizing doesn't matter. They both are the same word. So cis, 1, 2, they're the same substituents. We use di. They're methyl groups. I have 5 carbons in a ring. So cyclopentane. So what I'm doing is I'm putting cis out in front. I am putting a dash there because I'm then writing a number. And both of those top two would have that same name. This bottom one, trans, 1, 2, dimethyl, cyclopentane. Oop, I stuck an extra letter, pentane. So we're just designating which stereoisomer it is by putting the cis or the trans out in front of the name. So name it as you normally do, and then look, are the two substituents on the same side of the ring? If it is, it's cis. Are the two substituents on opposite sides of the ring? If that's true, then it's trans. If you have more than 2 substituents, then we can't use cis trans. We're going to run into that with alkenes later on in the semester. And instead of using cis trans, we're going to use a different designation, right? Because if I was to look at an alkene, right? An alkene, remember, is our functional group with that double bond in it. And if I wanted to go and put, actually, let's just leave those as hydrogens. That might be easier to see. I just want you to see kind of why, right? I'm putting those, there's hydrogens on the ends too, but I'm not including those. The other way I could do it this time I'm going to put my hydrogens in those positions. So what I'm trying to show is that anytime you have a molecule that you can't freely rotate, right? If I go and I look at my cyclic structure, we'll just draw one here. Because they're all connected, and I showed this in that intro video, I can't freely rotate it. I can move the bonds a little bit, but it's locked in place. if I have an alkene, right, if I have a double bond, remember those double bonds are made up of a sigma bond. So I'm just looking at these two carbons here. So they have a sigma bond, and then they also have a pi bond. And because that pi bond overlaps on the top and the bottom, it's locked in place. I can't rotate it because of that pi bond, right? If it was just a sigma, right, it overlaps in one spot, I can rotate it. But if I tried to rotate an alkene, I would have to break that pi bond because it locks it in place. So I'm actually going to have cis trans isomers with alkenes also. So anytime you limit the rotation of the molecule, so either with a ring or a pi bond, it doesn't have free rotation. So if I look at this one, if I was to draw a line right through that pi bond, my two methyl groups, this one and this one, are on opposite sides, so that's going to be trans. If I draw a line through my double bond on this one, my two methyl groups are on the same side, so that's going to be cis. I can't just rotate one to get the other because, again, I would have to break that pi bond. So we are going to run into cis trans isomers with alkenes as well as cycloalkanes. What I started to say is that as soon as I go and put like another group on here, I can't use cis trans anymore because now like two of those groups are cis to each other and two of them are trans to each other. So we're eventually going to use a different set of nomenclature, a different way to designate those. Cis trans only apply when it's di substituted. So di meaning two. I have two non-hydrogen groups. So two groups here that are not hydrogen. If we go back up and look at my cyclic ones, two groups that are not hydrogen. So two non-hydrogen groups, di-substituted, is where that's going to work for us. So let's do one example, and then we're going to be done with nomenclature, except for your practice. You guys are going to go practice this. You didn't mean to do that. This is going to be 7. 7's kind of hard to draw for me. You start out like you're going to draw a cyclohexane and then end like you're going to draw a stop sign. That's not too bad. And then I'm going to give it some stereochemistry. We'll just do a fluorine. Oops, some stereochemistry on that one too. Okay. So I usually do the cis trans after. It just leaves space for it. So I go through all the normal rules like numbering it. So I want the lowest numbers. So 1, 2, 3, 4, 5, 6, 7. My other option 1, 2, 3, 4, 5, 6, 7. So no matter how you do it, your substituents are going to be on carbon 1 and 4. Not that you can read that 4 in the pink, but in the pink, they're also going to be on 1 and 4. So when that happens, that's where we're going to pull out the alphabet. So fluoro. And then this is one of our special alkyl groups. What's that one? Yeah, good. Torpedo. If you didn't get that, I know you just learned them. Or were just shown them. You probably haven't actually learned them yet. So tert. And then butyl. Tert and sec were the two that had the dashes, which means for alphabetizing, I'm going to alphabetize this based on the B, not the T. And then this gets alphabetized based on the F, because the B comes before F in the alphabet. We're going to use the green letters, or green numbers. So that's my order. Tert, remember that stood for tertiary. If we go and look, right, this carbon here that's directly attached to the parent is attached to 3 other carbons. So 4 carbons total, right, 4 pink dots, so butyl. And then tertiary, because the bigger one, right, the one that's attached to the parent, is attached to 3. So putting my name together, I have 1 tert-butyl, 4 fluoro, cyclohept, because there's 7, and then ane, because it's an alkane. And then stereochemistry, I drew wedges for both of them, so that means they're both on the same side of the ring, so that makes it cis, and cis goes out in front. Remember, trans are opposite, cis are on the same side. I just remember that like cis and same side have the same sound, so cis, same side. That's how I remember that.